Dear colleagues, welcome you back to the lecture series on the theory of compilers. Our today's topic is syntax analysis. I'm going to speak about context-free grammars, parse trees, ambiguity of a grammar, and how to define associativity and precedences of operators in a grammar, and the basic concepts of parsing. As you could remember from the previous lectures, syntax analysis is the second step in the compiler next to the lexicon analyzer, and the syntax analyzer asks for tokens, and the lexicon analyzer provides a series of tokens, and the series of tokens is organized into a parse tree or syntax tree by the lexical analyzer according to grammar rules. As you could remember from the theory of digital computation, Church thesis proves that for any language defined by any grammar, there is a Turing machine which can accept the grammar, accept the language. And there are some general algorithms like the Koch-Younger-Kasami algorithm, which can derive the way of derivation by any grammar for any sequence of symbols. However, it is important to note that the more general a language class is, the less efficient deriving algorithms we have. That's why we are going to focus on mainly the deterministic pushdown automata, which can be easily implemented, and those languages which can be identified by deterministic pushdown automata. If we go back to the classes of languages, you could remember that regular languages can be defined by either regular expressions or regular grammars, accepted by finite state automata, and as an example is the E star, B star, so the language containing strings starting with any number of A's and followed by any number of B's. The second class is the context-free languages, where the language can be defined by a context-free grammar and accepted by a pushdown automata. And as an example, you can remember the language of strings A power to the n, B power to the n, where the same number of A's is followed by the same number of B's. And in general, you can have a general grammar for the general class of languages. Its specialty is that the grammar rules are not necessarily context-free, which means that around the at least one non-terminal there could be additional symbols that we have to match in order to apply a derivation rule. And these kind of languages, which can be defined by general grammars, can only be accepted by Turing machines. As an example, AN, BM, CN, DM, where n number of A's is followed by m number of B's and followed by n number of C's and m number of D's, is a special class of strings where A's, B's, C's, and D's follows each other in this order. However, the number of A's is equal to the number of C's and number of B's is equal to the number of D's. And these strings cannot be specified by neither context-free grammars nor regular grammars, only by general grammars. It is important to note that we are focusing on context-free grammars, for which we have efficient parsing algorithms, as you will see later on, can be executed on pushdown automata. And it is also important to note that most programming languages can be described by context-free grammars. For example, languages like Java, C#, JavaScript, and also C and C++, except the preprocessing part. So in the case of C and C++, the preprocessing, including the macros defined, cannot be described necessarily by context-free grammars. However, all the remaining steps after the preprocessing can be described as context-free grammars. For example, if you look at the GNU C and C++ compilers until the version 3, all these compilers have been created by parser generators. So practically the language was defined by grammar rules, and the syntax checking was generated according to the principles that we are going to learn during this subject automatically. In the case of syntax analysis, we have to take care of the errors and error messages as well. During any kind of error handling, the errors have to be clearly defined. However, recovery has to be quick to be able to check additional problems and not to slow down the compilation of a correct code. In case of syntax analysis, 4 different classes of error recovery strategies are applied. One is panic mode, when a whole block is ignored when an error is identified inside the block. Block can be a line of source code, or block can be defined by a series of lines of code between like begin and end pairs in Pascal-like languages, and between opening and closing braces in other languages. In the case of phrase level recovery, we assume that if an error occurs, it is caused by a typing mistake in the nearby area of the source code. So we are going to, for example, change commas and semicolons, or insert a semicolon, or ignore a semicolon, and local changes like this. Error production can only be applied at this level, I mean during syntax analysis, because in this case typical errors are implied in the grammar rules. So we define such grammar rules which leads to series of tokens in a typically faulty way. However, in this case, the application of these additional rules leading to incorrect sequences of tokens, we can clearly identify what the error was. And theoretically, the most useful could be the global correction, where the entire source code is modified to be compilable with minimal modification. However, it is computationally highly expensive and practically never applied. How the syntax can be defined? As I mentioned, we are going to apply context-free grammars in a less formal way than we used to during the theory of digital computation. So the context-free grammar contains tokens as the terminal symbols, and we have non-terminal symbols for the definition of rules, since every rule has a single non-terminal on its left-hand side and a sequence of terminals and non-terminals on the right-hand side. And somehow we have to define which is the start symbol. And in this subject, Theory of Compilers, we are going to list the rules only in a way that the first rule is defined for the start symbol. So for example, here we have a list of 4 rules, and the left hand side of the first rule we have the non-terminal list, and that's why it is considered to be the start symbol. And all those symbols which are listed on the left hand side of any rule are considered to be non-terminals, and the remaining symbols are considered to be terminals. And a sequence of tokens can be generated in a way that we start from the start symbol, apply a grammar rule, which means that we replace the non-terminal with the entire sequence on the right hand side of a rule where this non-terminal was on the left hand side, and then in the resultant sequence of symbols we try to replace the non-terminals by additional rules, changing the non-terminals to the right hand side of the rule again, until we have such a sequence which contains terminal symbols only, which in this case, since in the theory of compilers the terminal symbols are the tokens, so until we have a sequence of tokens. Let's see an example. For example, we had this for rule here, list to list plus digit, list to list minus digit, list to digit, and then digit to the number symbols from 0 to 9. According to these rules, for example, 9 is a list because it's a digit, and digit can be a list, and 9 can be a digit. And according to rule number 2, 9 minus 5 can be considered as a list, because 9 is a list and 5 is a digit, and list minus digit is considered to be a list, and so on. And the sequence of derivations can be represented on a parse tree, as you can see here, where the star symbol is at the root of the tree, and we have non-terminals at any intermediate nodes, and we have terminal symbols, so practically tokens, at the leaves. And for each intermediate nodes, if we read its children from left to right, we should get a sequence of symbols on the right hand side of a rule, which can be applied to the non-terminals. So for example, if we have children like list, minus, and digit for non-terminal list, it means that there could be a rule in the grammar like list to list minus digit. And at any point where we have a non-terminal and a series of children, the non-terminal is considered to be the left-hand side of the rule, and the children in the same order on the right-hand side of the rule. Let's see another example here, where we have list as a parent and list, plus, and digit as children. So it corresponds to the application of grammar rule list to list plus digit. And the tree is complete if we have only terminal symbols, so tokens at the leaves. Okay, this kind of application of rules and their representation in the parse is described in detail here. Finally, we get a so-called parse tree, which starts from the start symbol and finally leads to a sequence of tokens, where at each intermediate node a grammar rule is applied to get its children. A grammar is called unambiguous if there is more than one if there is more than one parse tree from the same sequence of tokens, for a single sequence of tokens, then we say that the grammar is ambiguous. So in this case, there are at least two different ways of constructing a parse tree, so at least two different ways of applying grammar rules and getting the same sequence of symbols. And in this case, as you will see later on, we cannot construct a deterministic algorithm which leads to only a single parse tree, since any parsing algorithm should result all the parse trees, and if there are multiple of them, then it should list all of them, and as you will see later on, it considers some kind of backtracking and resulting in a parse tree, continue the search to the next one. How we can make a grammar unambiguous? For example, if the grammar includes operators between other tokens, then we are going to follow the rules what we have learned in math during the primary school. For example, we are going to take into account the associativity of the operators. That, for example, if we have multiple plus and minus operators, so addition and subtraction, they should be applied from left to right. So in this case, those parts on the left should be closer to each other in the tree, which means that practically they are closer to the bottom of the tree, so they are lower than the remaining part. And as it is represented by left recursive rules, as you will see. And similarly, if we have the assignment operator, which is evaluated from right to the left, then the right hand side of the expression should be lower in the parse tree, where to enable us to evaluate the expression button to the top and get the result what we used to get, for example, executing a series of assignment operations in a programming language. As a result, from the less associative operators, we have grammar rules with left recursion. Left recursion means that we have such a rule for a non-terminal which includes the same non-terminal of the leftmost in the leftmost symbol on of the right-hand side as we have at the left-hand side. And similarly, here we have another rule where we have the same symbol as the leftmost symbol of the right-hand side, which is at the left-hand side. So recursive because the right-hand side contains the same symbol as the left-hand side of the rule, and left recursive because this symbol is on the leftmost symbol on the right-hand side. In the case of right associativity, like at the assignment operator, we get right recursive grammar rules. It is recursive because we have the same symbol on the left-hand side and right-hand side, and this symbol is applied at the rightmost end of the right-hand side. And the resultant syntax trees looks like this, that in the case of less associativity, the left branch is extended further and further with the length of a series of left associative operators, while in the case of right associative operators, the right branch of the tree is extended further and further. And if we evaluate these trees from the perspective of the tokens, so practically from the bottom, you can see that 9 and 5 are closer to each other in this tree than, for example, this part 5 and 2, and that's why this 9 and 5 is with the corresponding operator is evaluated first, and then the remaining part. In contrast, for the assignment operator, B and C are closer to each other than any of these two to the A. So first, the B equal to C is executed first, and then the result is taken into account with an assignment operator to the A. Okay, and if you are going to evaluate expressions containing operators of different levels of precedences, then associativity is not enough. Somehow we have to clearly define the precedence of the operators, and the purpose is the same. Define the exact order of the execution of the operators, and as I mentioned, it is to be done in a way that those parts evaluated first have to be lower in the syntax tree. So for example, if we have 9 plus 5 multiplied by 2, then this 5 multiplied by 2 should be at the lower part of the tree, and certainly the 9 plus 5 multiplied by 2 is not as described here, where the addition is executed first, but it is to be evaluated as represented here, where the 5 multiplied by 2 is executed first. And the solution is that we introduce different non-terminals for different levels of precedences. For example, we call the expression where a series of additions and subtractions are applied. We call the level, we identify the next level with the non-terminal term, where multiplication and subtraction is applied. And finally, we identify the third level with factor as a non-terminal, where we have digits and expressions in braces. And as you can see here, as we go down in the syntax tree from top to the bottom, the precedence of operators increases. So in each case, we can go from expression to term and term to factor. So we can go from a lower level of precedence to a higher level by deriving the higher level from a lower level non-terminal by a rule, and it ensures that the parts with higher preferences will be lower in the parse tree, and that's why it can be evaluated first and the lower level later on. And the steps which shows how a certain series of derivations have to be applied to get the series of tuples is called parsing, and it implicitly defines the parse tree as well. And there are two main classes of techniques to set up a parse tree. One is top-down, where we start from the start symbol and goes to the direction of the leaves or trocans, and the other in the parsing algorithms in the other class starts from bottom to the top, which means that first we start with the tokens and try to discover how they could be derived from which non-terminal and go from the bottom to the top till we reach the start symbol. So practically in the case of top-down translation, we try to find the rule to be applied to a non-terminal. In contrast, in the case of bottom-up parsing, we try to find those rules which leads to a certain token, and later on we are going to find how the non-terminal on the left side was derived. In general, top-down techniques are easier to implement, and bottom-up algorithms can handle more complex languages. So, in this presentation, I have introduced the simple way of definition of context-free grammars, which is to be applied during this class. I had introduced the parse trees and what ambiguity means in case of grammars, and I have shown how to describe in the language if an operator is associativity of operators and precedence of the operators. And finally, I have defined the term parsing, which means the identification of the sequence of derivation rules leading to the sequence of tokens to be analyzed during the syntax analysis. Thank you for your attention.